All right, welcome to video 6. In this video, I'm going to be discussing transformations of sine and cosine. We have established sine and cosine as functions, and we have looked at their parent graphs. But now it's time to kind of look at how can I transform these basic waves so I can use them to model real-world problems, which we will be doing in the next video, as well as the project I'm going to assign you in between these two videos and kind of to do for the middle of the week, Wednesday and Thursday. And so before we get into that, I kind of want to highlight a couple of key ideas, specifically what's called the 5 key points technique, because I need a pretty efficient method in order to sketch these, because again, the goal here is to sketch. We're not getting a complete graph by hand. And I don't want to have to go through and plot every single special angle like we did when we initially came up with the graphs of sine and cosine. And so my goal here is to only use 5 key points. And these key points are actually shown here on this basic unit circle that I've got drawn on the right-hand side. And the 5 key points that I'm going to be using are the radian measures of 0, pi over 2, pi, 3 pi over 2, and 2 pi. And the reason why I'm using these, and hopefully you could take an educated guess towards this, is that each of these points, each of these radian measures occur at the extremes of the circle, right? It either covers the far right and far left, or the far up and the far down in terms of these coordinates, meaning we are maximizing and minimizing my x and y coordinate specifically. And the reason why this is so important is if I wanted to say graph y is equal to sine of x, all I need to do is know what sine is doing at these 4 points, and then I could get a basic sketch as long as I know that sine is a wave and that it's going to be symmetrical. And so what I'm going to do is go straight to my graph at this point, and I'm going to mark my 5 key points. So 0, I'm going to put pi over 2 right here, pi, 3 pi over 2, and 2 pi. So I'm going to keep it kind of short. All right, and I'm going to go through and just evaluate or look at the unit circle for each one of these angles. So for example, at 0, sine is going to be 0. All right, it's the y coordinate at that radian measure, which means I am going to start right here at the origin for sine. Now, the next most important key point would be at pi over 2, because that is where sine has reached its maximum value of 1. So if I go here, I'm going to mark 1 on my y-axis, and I'm going to put an ordered pair for pi over 2, 1. When I get to pi, sine of pi is now 0, so that means I've gone now back to the middle for pi. And then at 3 pi over 2, sine has reached its far minimum, which would be -1. So I'm going to put a dot down there at -1 at 3 pi over 2. At 2 pi, we've recycled, and I'm now back to the middle. And now I've completed my 1 cycle of the wave, which I'm now going to sketch in. And here is 1 cycle for sine. I know that if I wanted to get more pictures of this wave, like if I wanted to extend this past 2 pi, I know that because of the feature for sine, I can literally copy this and paste it and just attach this to the end, and then I can continue getting more and more pieces for sine. Here would be another piece, etc., and the wave would just continue because it's all repetition given that this is a circle. So I'm just going to get rid of that stuff so we go back to the 1 cycle. And so this would be how I could graph sine using the 5 key points technique. For cosine, I'm going to use these same 5 points, and so I'm going to go through and graph now 1 cycle of cosine. Again, noting that cosine maxes out at 1 and -1 as a min. And I'm going to mark 0, pi over 2, pi, 3 pi over 2, and 2 pi, like we did before, using the same 5 key points. All right, now cosine is referencing the x-coordinate as I travel around the unit circle. So at 0, the x-coordinate is 1. So I'm not starting at the origin like I am with sine. Cosine is actually starting at its maximum. Because then as I go to pi over 2, the x-coordinate goes down to 0. And so my ordered pair is now in the middle along the x-axis. When cosine gets to pi, I've now hit -1. So I've decreased down all the way to its far left on the unit circle, or its far bottom when I look at the graph of cosine. And then by the time I get to 3 pi over 2, cosine is increased back to 0. If you notice, that is your x-coordinate. And then when I come back to 2 pi, I'm back to 1. I've reached the peak again. And so when I graph cosine, like I mentioned in the previous video, cosine looks a little bit more like a V, just curved. And so cosine looks like this. And then again, if I wanted to get more cycles for cosine, just like last time, I could take this graph and literally copy and paste it and just continue to attach this over and over and over and over, and I would get the continuation of the wave to the right and to the left. But in order just to get one cycle, this is all we need. We just need to know 5 key points. And if we're getting really specific, we can choose those 5 key points to be literally the max and mins for my wave, as well as when I'm in the middle. The midline is how I'm going to refer to this later on. These are my 5 key points that we're always trying to find because I know that these points are going to tell me when I'm going to crest and when I'm going to valley in terms of my wave, so my crest and my valley, as well as when I'm going to hit in the middle. And if I can figure out again what these are, I know that this will always cycle. So for example, if I know that sine is starting here at 0 and it's going to go up at pi over 2 to 1, I know I have to come back down and be in the middle and then continue going down because I have to finish the wave and then back to the middle. So these points are essentially alternating as I go through. It's the same thing for cosine, right? But cosine will start at its max. And because I'm at my max, I must go down, which means I have to hit the middle. But then I have to continue going down to hit the min. And because this is the min, I have to come back up to then complete the cycle. All right, it's a circle, right? We have to complete this cycle. And that's why the 5 key point technique is so important and so efficient when it gets down in and solving this. And so the last thing that I want to mention, and this is going to be a really important idea when we're trying to do these by hand, or if I'm trying to go through and at least figure out, based on a graph, how to write the equation, is that because this is a circle and because of symmetry, these maxes and mins, these 5 key points, they always occur at equal intervals. Right? Just like how this unit circle right now, with the way that my ordered pairs are chosen, right, by the radian measures that we're focusing on, these are all radians that are equally spread out. We've taken the circle and essentially quartered it, right? I've created 4 equal slices. And if I look at my radian measures, if I look at these 5 key points, the differences between these are all the same in terms of the lengths. We've taken this overall measure of 2 pi and I've broken it into 4 individual pieces, 4 intervals. And notice that these intervals, not pi over 4, would be pi over 2. And so if I know my starting point, which in this case is going to be 0, notice that each dash mark is gained by adding pi over 2 to each point. Each step would be pi over 2. And in terms of this formula, I notice that 2 pi is 1 cycle, which we've known and talked about how that means period. And then I'm always taking the period and dividing it or breaking it up by 4. Thus, I need 5 key points to create 4 different intervals, right? 4 different sections. But it all starts with knowing that 1 cycle for cosine is 2 pi, and knowing that 1 cycle for sine is 2 pi, and breaking that up 4 different ways. All right, now understanding these 5 key points technique, understanding the basic graphs of sine and cosine, we can now go through and actually look at applying some transformations. Specifically, we're going to start with shifts, and then we're going to hit on some vertical stretching. And then in the next part of the video, we'll talk about horizontal stretching and then put it all together into one general format. All right, and so let's look and focus now on 2 different types of shifts, which would be a horizontal shift. Whoops, I thought I had my laser pointer. My horizontal shift. So can I take a graph, can I take a wave and move it to the left or right, essentially changing its starting point? And will I be able to take a graph and move it up and down, essentially creating a vertical shift? Where can I change the middle, the midline, and what does that look like? All right, and so in the first example, because I'm going to do this with numbers, because I think it'll be easier to look at that way, I want to take the original graph of sine of x, and I want to shift it pi over 3 units to the right. So I don't want to change the middle. I'm not going to change the shape. I literally just want to pick it up and move it pi over 3. All right, now what that's going to do is instead of starting it at 0, which is where sine originally began, this new starting point is going to be pi over 3 units to the right. So I'm going to move this point to pi over 3. And I'm just going to pick a spot because I'm just going to sketch this. Well, I know that in total I should have 5 key locations. The pi over 3 tells me my first location, so I should have 4 more dashes. And not only that, like we talked about, those 4 dashes have to be in equal intervals. So I'm just going to sketch, I'll use the lines that I have on the graph paper. So I know that has to be equal. So this is 1, 2, 3, 4. Notice now I have 5 total dash marks, but I have 4 intervals, 1, 2, 3, 4. So what that means is if I want to figure out what these markers are for this new graph, I know that 1 cycle for sine is worth 2 pi. I'm going to divide this by 4, and I now see that every interval I'm going to add pi over 2. That's the length for each one. So if I'm starting at pi over 3, to get to the next dash mark, I need to add pi over 2. Well, this involves adding fractions, so I need to get this to have a common denominator. So that common denominator will be 6. So to take something that's pi over 3 and get it to be something over 6, I need to multiply top and bottom by 2. This means this will be 2 pi here. And to rewrite pi over 2, I need to multiply top and bottom by 3. So I have 3 pi in the second one. And this means that the next dash mark has to be 5 pi over 6. So I'm going to list that and fill that in now. Now, we generally only have to walk through this process once because, again, if I'm going to get to the next dash mark, I'm going to add another pi over 2. But because, again, we need a common denominator, I'm not really going to add pi over 2. I'm going to add 3 pi over 6 because that's its equivalent. And because this denominator is already over 6, this is now the same. I can just add 3 pi to the numerator consecutively until I get to the end of my graph. So the next one would be 8 pi over 6. The next one would be 11 pi over 6. The last one would be 14 pi over 6. And now I have all of the dash marks listed from the original 5 key points that are now shifted to the right, pi over 3 units. And once I get everything written out, you may go back through now and look at it and say, okay, well, you could have simplified this one. You could have simplified this one. Now go through and simplify. And the reason why I didn't simplify to start is that if I took 8 pi over 6 and I rewrote it as 4 pi over 3, which is its equivalent, remember I'm adding pi over 2, so I would have to do the exact same thing we did here, and I'd have to go through and find a common denominator again, and then go through and do all that process. Well, again, it's over 6, so why not leave it in terms of its improper fraction, non-simplified form, so that way I can continue adding a really basic 3 pi over 6 each time until I get to my end. And this is honestly probably one of the hardest things to do when it comes to sketching sine and cosine. You're not going to be asked to do this very often, which is very nice. We're just going to see this in practice right now. But the goal here is to hopefully come up with a way, uh, so if you needed to sketch this by hand in the future, or really just come up with a general formula. Um, so let's continue going through. We still haven't sketched sine of x. All this work was really just to find what my dash marks would be, like the locations. And so let's look back at the original graph of sine. And again, know that at my starting value, which was originally going to be 0, we started in the middle. Whoops. We started in the middle. I'm going to do the same thing in this graph, but my starting point is now pi over 3 here. And we know then that at the next dash mark, sine goes up to 1. So when I get to 5 pi over 6, I know I'm going to go up. Then that means I have to come back to the middle, but then I have to go down to the min, and then I have to come back. It's this alternation. And sine will always do this because sine goes up, starts in the middle and goes up to its max, then back to the middle, down to its min, back to the middle, right? Sine is a wave that actually looks like a wave here. And now I've graphed one cycle of sine that has now been shifted to the right, pi over 3 units. And just to kind of see the shift, and I won't actually put it up, I would encourage you to test this in Desmos. Go through and actually graph in Desmos this function sine of x being shifted. Well, this is where you're going to have to recall what we've done in mod 4 at the very, very beginning. That if you want to create a horizontal shift, I'm going to add or subtract on the inside affecting x, right? It's all about being on the inside of the parentheses. So for this one, if I want to shift pi over 3 units to the right, then how I need to write this is sine x minus pi over 3. This is going to take the original graph of sine of x and literally shift it to the right. And this point, again, right here, this pi over 3, this represented where we started in terms of my x values. Because originally, if we're always going to start at 0, then that means this new point is always going to be the next value. All right, so now let's look through and let's do a vertical shift for cosine. All right, let's go through and shift cosine. Let's do 2 units up. So this time we're not shifting to the left or right. So let's go ahead and go to my graph. I'm going to move this off of the page break. There. Actually, never mind. All right, and in this kind of example, notice how we're not shifting left or right. So that means the dash marks, my starting value is going to be at 0 because I'm not moving it, right? I'm not moving it left or right. I'm only moving this graph up. So that means my dash marks 0, and then the 4 equal points after that are going to be the same as normal. Again, this is because I'm not shifting it left or right. I'm not changing my starting x value, right? My starting x value will be 0. Now, what will change is where the middle of this graph is. All right, for example, if we look back at the original graph for cosine, the original graph of cosine starts at its max, which is normally 1. But remember, I am taking this graph, this entire blue line right here, and I am moving it 2 units north. So instead of this starting at 1, it is now going to start at a y value of 3. So I'm going to go, so let's see, 1, 2, 3. And at 0, this is where I'm going to put my first point at 0, 3. And now again, this is the maximum for cosine. So I know that it will now go down Well, how many steps does it go down? Well, let's look back at the original graph. In the original graph, we go from 1 to the middle, which is at 0. So we take one step down. So if I'm starting at 3, I'm going to take one step down to 2, which means then at pi I'm down at my minimum, which will now be 1, back to the middle, and then at my peak. So the graph of cosine that has been shifted 2 units up would look like this. And so it's really important here to notice that if I wanted to cut this graph in half, the line that would represent the middle is at 2. And so the observation and the generalization then is that when you shift something up or down, what you are affecting is the middle or the midline of your sine or cosine graph, right? So if I was to shift up or down, this is my middle. And so what's really helpful about that then is if I know where my middle is, a basic sine and cosine graph is always one step up and one step down from the middle because of the unit circle, right? The unit circle only has a maximum and a min of 1 in either direction that you're going to travel. And so once I know where my middle is, I can take that one step up or one step down in order to create the wave as I go through and work a problem of something of like this caliber. And so again, what I want you to do is to go into Desmos and to essentially graph cosine of x, which is the original function. And then I want you to graph this transformation just to confirm what we're seeing here and that this graph has now been moved completely up and its shape has not been changed. Well, how do we go through and write this in, right? What function do I type in? Well, recall that if we're doing a vertical shift for functions, that means I'm going to take my original function and add or subtract on the outside of that function. The k represents the vertical shift. So in this kind of problem, I would type in cosine of x and then I would add 2 on the outside because I don't have to worry about the sign changing or anything like that when it came to horizontal shifts. Right, so just kind of keep in mind anything on the inside is always backwards. So again, when we looked at our horizontal shift, I wanted it to move to the right, so we subtract on the inside. But if I want to vertically shift something up, this follows like normal. I want to go up. It's on the outside, therefore I'm going to use plus 2. And so this is the two basic shifts when it comes to sine and cosine. We're not changing the shape of the graph. We're only moving either its starting point by horizontally shifting this or vertically shifting, changing where that middle or the average, the midline of my sine and cosine graphs are. Okay, and so to go through and do some practice with this, I have an example set up here, which is to describe the transformations and then sketch at least one cycle using Desmos to check your sketch. So being able to type this in and kind of compare between the original function and your result and see did it match your description. So feel free to pause the video here and go through and attempt each of these problems. I'm going to go through and walk through the description. And I'm really only going to show you, well, and I'll show you how to sketch it. I'm not going to go into major detail of how to sketch it and really walk through every individual step. So if you need some more explanation, definitely let me know during virtual class time or during my office hours. I'd be more than happy to walk through either these examples or other examples with you. All right, so go ahead and attempt these and then hit play when you're ready to see these problems worked out. Okay, so I'm going to go through and do A. So I've got y is equal to sine of x minus 2. So because of the subtraction 2 on the very outside, I know that this is a vertical shift down 2 units. And so if I want to sketch one cycle for this, I know that my midline is going to be at -2. So here, this will represent the middle of my graph. All right, I also know that because I'm doing just a vertical shift, my starting x value is going to be at 0. And then I'm going to have 4 more points after that to represent my 5 key points. Now, I'm not changing the period at all. So my period is normally 2 pi, and I'm breaking this up into 4 equal pieces. This is what I call my intervals. So that means that is worth pi over 2. So starting at 0, adding pi over 2, I get pi over 2. Adding another pi over 2 would get me to pi, 3 pi over 2, and 2 pi. And so now I want to create my sketch for sine. Sine always starts on the midline, so I know I'm going to start at -2. And then at the next dash mark, I'm going to hit my highest point, which is 1 step higher. And then I have to come back to the middle, go down to my lowest point, and then back to the middle. And now I can connect the curves. And here's 1 cycle for sine of x minus 2. Literally the exact same wave, just now being shifted down 2 units. Notice that my maximum here is now at -1. The minimum is -3. Both of these values are 2 steps below what they normally would be. So here's how you'd solve A. Okay, for B, I have y is equal to cosine of x plus 1. So this is a vertical shift up 1 unit. My starting x value is going to be 0. I'm not shifting left or right. And this means that my intervals for my 5 key points would be the 1 cycle, which is worth 2 pi, divided by 4, which is pi over 2. So my dash marks are going to be the same. So I'm going to go through and draw my x and y axis. I'm going to go through and put in my midline. So my midline is here at 1. And then I'm going to put in my dash marks. So this is 0. The next step would be plus pi over 2, then pi, 3 pi over 2, and then 2 pi. And cosine begins at its highest point. So if my midline is at 1, then going 1 step higher is where my cosine graph will begin at 0. So that means my highest point is now 2. Then cosine comes back to the middle, and then down to its lowest point, which will now be at 0 in terms of a y value. Then back to the middle, and then back to its highest point. We're taking 1 step each, because that is the max and min for the unit circle. And so here's the graph of cosine that's been shifted directly up 1 unit. All right, let's take a look at C. This is y is equal to sine of x minus pi over 4. Now in this problem, there's no vertical shift. This is just a horizontal shift, specifically pi over 4 to the right. So that means my starting x value, my starting dash mark is no longer at 0, but at pi over 4. Now my intervals are still going to be 2 pi over 4, which is pi over 2. So if I come over here to my graph, there's no vertical shift, so my midline is the x-axis. But my starting dash mark for my 5 won't be at the origin. It's going to start at pi over 4, which I'll put right here. And then I need to mark 4 extra steps for a total of 5. And these are going to represent my 5 key points, but I need to know what these 5 key points are. Now each one is an equal interval. We found what that equal interval is. So I need to go through and say, all right, well, if I'm starting at pi over 4, I need to add pi over 2. Well, to add these two things together, we need to have a common denominator. That common denominator is 4, which means for the first, I don't need to change that at all. I'm just multiplying by 1. But for the second one, I'm multiplying top and bottom by 2. And this tells me that the next dash mark has to be 3 pi over 4. Now to get each next mark, I'm continuously adding pi over 2, which is worth 2 pi over 4. So the next mark would be 5 pi over 4, 7 pi over 4, and then 9 pi over 4. That's my final mark. And now I'm going to go through and graph sine. Now sine again always starts in the middle, and my starting x value is pi over 4. So at pi over 4, I'm starting on the midline, which is the x-axis. And then now I'm going to begin alternating where sine goes to its max, which is 1 unit, then down to the middle, down to its lowest point, and then back to the middle. And now I'm going to complete my wave. Highest dash mark is 1, lowest dash mark is -1. So hopefully you're kind of picking up the steps here in terms of how to go through and essentially sketch these. In terms of a process, what I like to do is I like to go through and work on my description, but I essentially start with where is my middle. I go through and do my 5 key points, aka you need to find your intervals, and then I begin to walk the wave. And this is what I'm always going to do when it comes down to it. Key parts, again, to remember with this is that sine always starts on the midline. Cosine always starts at its max, or off of the midline, always. These two things are always true. There's one small thing that'll change it, and we'll see that a little bit later. All right, so now you'll notice for this previous example, I've only done A, B, and C. I'm going to stop here at this point just to kind of move on with the video. I've worked these out in my lesson plan, so feel free to take a look at the work that I've done for this. I just won't go through and describe it. I may do, I think I've got some space here. I'll make some space for at least to do E to show you one that's got multiple combinations, but then I'll leave you F to try on your own, and then check work essentially in the lesson plan that I have posted for trigonometric functions 2.2. All right, so here's what I'll do. I'm just going to move this down a little bit to make some space, and let's do E, which is y is equal to sine of x plus pi over 2. And then I forgot the other shift. Minus pi over 4 minus 2. So this was minus pi over 4 and then minus 2. All right, and so in this kind of function here, this has a horizontal shift of pi over 4 to the right and a vertical shift down 2. And the way that we translate these two things in terms of sketching is that the horizontal shift tells me my starting x value is going to be pi over 4. And the vertical shift tells me that my midline is -2. So that when I come to my graph, I'm going to first start with my midline. I'm going to go to -2 here. I'm going to draw a dotted line across, dashed line, I guess. And then for my x's, I'm just going to put a mark here at pi/4, and then mark 4 more points for a total of 5. Now to figure out what those 5 key points are, I'm going to take pi/4, and I'm going to add to it the intervals. Well, remember to find the interval, I take my period, which in this case is 2 pi, and divide this by 4, and I get pi/2. Now hopefully you're kind of asking yourself, well, this is what we've gotten every single time. So therefore, shouldn't I just go ahead and just add pi/2 to start with? And the answer to that is yes. That is what we're going to do, especially in the next section as well, because we're not changing the graph horizontally. We're not affecting its period yet. All right, and so for now, you can pretty much go through and always do this and just say that it's pi/2, but I want you thinking through in this idea of do the midline, do your 5 key points, and then think about the intervals even in these simpler cases. So I'm going to go through and add pi/2. Well, we've done this before. This is adding 2 pi/4. We've already done these intervals, so I'm going to go ahead and list them in. So that way I can get to doing my ordered pairs. And so we've got sine, which always starts on the midline. Then it goes up 1 unit, back to the midline, down 1 unit, back to the midline. Here's the graph of sine of x minus pi/4 minus 2. It is a graph of sine that has been shifted to the right pi/4 and down 2 units. And here's my 1 cycle. All right, now with this, we essentially then have a general form being made. And this is what we're going to continuously kind of add to. For right now, we have y is equal to sine of x minus h plus k, or y is equal to cosine of x minus h plus k. H represents the horizontal shift, which we translate as my starting x value. K represents the vertical shift, which is the middle or the midline for my wave. So this is where we're at so far. This covers both types of shifting, horizontally and vertically. So as you can see, the next topic is essentially this, which is vertical stretching. So in the previous problem, in this previous example here, I said, okay, well, sine starts in the middle, and then I go 1 step up, 1 step down, 1 step down, 1 step up, right? It's always this distance here of 1 unit. Well, is there a way to stretch this, treating it like a rubber band? If these right here were nailed in to the middle, can I stretch this point and this point to the same magnitude? And if you want to do any kind of vertical stretching, remember that what you're essentially doing is multiplying on the outside of your function. I'm taking all of the original y values, which is what f of x represents, and I'm multiplying them by a factor of a. So for example, remember that if you saw something like 3 times f of x, what this is doing is taking all of the original y values and tripling them, right? So if you had a y value at 1, it's now at 3. But if you had a y value at 3, it's now at 9, right? It's not just shifting something up 2 units and the spacing is remaining by 2. Everything is changing by a factor of 3. And so for trig functions, it's actually the exact same thing. All right, so just to kind of get rid of this stuff here, let's say we just took a basic sine function, sine of x, and I said, well, let's multiply this by 2. So let's put a 2 out front. Well, what this is going to do again is it's going to take all of the original sine values, whatever those outputs are, and it's going to double them. All right, well, what I'm going to do is let's go up and I'm going to take the original sine graph that we did up here. I'm just going to copy this real fast. And I'm going to come down here to our problem and paste it. Make sure I got enough space. Okay. All right, and so what I'm going to do is let's walk through, and I'll use a black pen for this. Let's go through and essentially now double all of the y values for our 5 key points. Well, we first started here at 0. Well, 2 times 0 is still 0, so the middle point doesn't change. But what happens to the point at pi over 2? Right, this maximum location right here has a y value of 1. Well, I'm going to double that. So it will now be at 2. Well, sine then comes back down. Well, the midline is still here at 0. 2 times 0 is still 0. Well, what happens to the lowest point, though? Negative 1 times 2 is negative 2. So this point now gets stretched. Because again, the midline does not change. So these middle points here, here, and here don't move when you're multiplying something on the outside. All this 2 is affecting are the maxes and the mins. And specifically, what it is describing to you is what's known as the amplitude. This is the distance between the max and min of a wave to the midline or the middle. And in terms of my general format, that is what this A will represent. So in a basic graph for sine and cosine, if you have A sine of x or A cosine of x, what that A directly represents is the amplitude. It tells you exactly how many steps to get back to the middle. So for 2 sine of x, that was a length of 2. All right, so take a look at this example here. I've got 2 functions to specifically look at. Doesn't matter right now whether they're sine or cosine. Let's just go through and see if we can figure out what is the amplitude and where's the midline for each of these graphs. Now the middle I think is the easiest one to find. All right, so let's look at A. I'm going to zoom in a little bit so we can kind of see it a little bit better. All right, now I want to cut this graph perfectly in half. All right, well, one way to do this is to note where the max is and where the min is. So the max is at 1. That's this value. The min is at negative 3. Well, I need to find the middle in between 1 and negative 3. So to find the middle, we just average those 2 values together. And this is when we talk about midline, we can think about this as the average between the highest and the lowest points. Right? I can take 1 and say plus negative 3. And because I'm adding 2 things, let's divide that by 2. So I get negative 2 divided by 2, which is negative 1. That's where my midline is. And you could have also taken a guess and looked at it and just sketched this in, and that's really helpful when I have the line. So here's my midline. There's the midline. There's the middle. It occurs at 1. Well, what's the amplitude then? Well, the amplitude is the distance between this midline and the highest point, or the lowest point. So in this problem, the midline is this distance here. Well, that's literally going from here, 1, 2. So the amplitude is 2. So I have a midline of negative 1 and an amplitude of 2. Well, if I want to write a function for this, I can do that, right? So let me get rid of this distraction here and here by first going through and noticing that here's my midline, and that this graph starts at the midline, goes up, down, down, and back to the midline. Well, which function does that, sine or cosine? Well, sine does that, right? So I can go through and say, okay, well, this is a graph of sine. Has it been shifted? Well, yes. Has it been horizontally shifted? No. How do I know that? Because if I look at the starting value that we have here, what's the x-coordinate there? So I know that on the inside it's x minus 0, because h represents my starting value. Now that's not subtracting anything, so I'm just going to put sine of x. But where's the midline? Well, that represents my k. The amplitude is what's being multiplied on the outside. Here's one way to write the equation. All right, let's take a look at the other one. Let's take a look at b. All right, so to find the middle, one technique again is to find where the max is. Well, the max occurs at 5. The min occurs at -1. And then I can average these two values together. Or when I look at the graph here, I can just cut this clearly in half. And I can see that the middle of this graph is 2. So there's my midline. That means the amplitude is going to be the distance from the midline to the highest point. Well, 5 minus 2 is 3. And there's my amplitude. So if I wanted to write an equation for this, then I need to go through and figure out, am I wanting to do this using sine, or am I wanting to do this using cosine? In this problem, it's a little bit trickier. So I'm going to be lame, and I'm not even going to write the equation for it. I just want to focus here in terms of our difficulty. All right, and so that's it in terms of doing amplitude. And so I want to add then to our general formula before we doing sketching with this stuff. And so, and then I'll have this even more so at the end. So right now our general formula contains the following, and I'll do this just for sine. A sine x minus h, and then plus k. All right, where the A is my amplitude, the h is my horizontal shift or my starting x value, and k represents the midline, which is my vertical shift. All right, so we have vertically stretched, we have horizontally shifted, and we have vertically shifted. So that leaves us then, as you can see in the next section, what about if I want to do horizontal stretching? What if I want to go through and essentially affect how quickly I'm completing this one cycle? And so every sine and cosine graph we have worked on specifically has had one single period. It has completed one cycle within 2 pi. That hasn't changed. All right, and so just as a reminder, a period represents the length that it takes sine or cosine to complete one cycle. This is the definition for period specifically and how we're going to be using it. And so what I want you to do is to go through and take a look at some different functions, specifically functions that are affecting x on the inside by multiplication. So we're just going to focus on sine because it is this format here that will ultimately affect the period of a trig function. Most of the times when we're working with applications, right, 2 pi is not going to be our period. If you think about seasons and how we can model seasons using waves, since it oscillates and it cycles, essentially creating a circle, one complete cycle would be 1 year or 365 days. Well, that's not 2 pi, right? And so how can we go through and make that adjustment? How does that work if I wanted to mathematically model? All right, and so here's what I want you to do. So you're going to go through, graph sine of x in Desmos. And then you don't have to sketch this. What I want you to do is go through and then graph sine of 2x, sine of 3x, and sine of 0.5x, and complete the table below. And then through this investigation, hopefully come up with a conclusion about how we can determine the period based off of essentially what we're multiplying here on the inside by what b is. Okay, so go through and complete this table. Again, use Desmos to do that. And then what I'll do is bounce back and forth and complete this table out. Okay, so I want to, okay, I got this pulled up. Okay, cool. All right. Step is going to be pi. Sine of x. Okay, so back at this point. All right, so 3, 2, 1. Okay, so I'm going to swap over to Desmos. And right now in Desmos, I've got graphed in sine of x. You'll see 0, pi, 2 pi, and 3 pi along the x-axis. Just a reminder on how to get that. If you click on the wrench to go here, if you go to your x-axis under step, if you type in pi or select pi from the keyboard, then that'll change your x-axis into radian measures, and that'll help us kind of answer the question. All right, and so the first part of this asked us to graph sine of x and then graph sine of 2x and then observe essentially what's happening here. And so again, the red represents the original function, and notice the blue is now sine of 2x. Essentially, what has happened here between these two? Right? And hopefully what you're seeing is that you're taking this original sine graph and is now getting squeezed and pressed together. And how we can kind of see that is, first off, essentially, what is the period, what is the length on the x-axis that it takes to complete one cycle for 2x? Well, if I start at 0, which is my starting point, this graph goes up, down, and back to 0, completing the wave by pi. So pi actually represents here my period. And so I'm going to put that in. Well, in the next column, and actually I'm going to change this to blue, just so it sticks out a little bit. All right, well, take a look then at its frequency. All right, look at the cycles within 2 pi. If I compare, so going back into Desmos, I'm going to put up the original graph again. The original graph here, it takes one cycle as 2 pi. Well, how many cycles of sine of 2x am I getting in that same time? Like, what's actually happened here? Well, sine of 2x is now twice as frequent. Notice I'm getting 2 full cycles now in the normal 2 pi, in the normal run. And so when I'm talking about angular frequency, and when I'm talking about frequency, that's what I'm talking about. How many laps, how many cycles, full cycles are we getting now in the original 2 pi? And so this is saying that we're getting 2 full cycles now. All right, we'll look at sine of 3x. All right, so let's go through and I'm going to change, I'm going to turn that one off. And I'm going to put in sine of 3x now. Now notice this is even squeezed in even more, so it's like literally like a slinky that's being pressed in. Well, what's the period of sine of 3x? All right, well, let's get rid of the original function so we can look at it. All right, well, notice if I'm starting here at 0, I go up, back to the middle, down, back to the middle. I complete one cycle by 2 pi over 3. So 2 pi over 3 is my period. I'm going to put that in. Oh, what's the frequency? How many cycles of sine 3x are we getting by the time the original function does 1? So going back to plotting these two things, again, here's the original function in red. It normally completes by 2 pi. Well, how many full cycles of the green am I getting? Well, I'm getting 1, 2, 3. So hopefully you're kind of seeing a pattern here. All right, notice that whatever b is the number for my frequency, right? Sine of 2x gives a frequency of 2. Sine of 3x gives a frequency of 3. So if I have sine of 0.5x, then the guess would be that my frequency would be a half, or 0.5. Well, what do you think the period would be? How long do you think it's going to take to complete one cycle? All right, well, let's take a look at the graph for this. I'm going to turn this one off. Let's put sine of 0.5 x in. And so notice that with this graph here, the original function is completed by 2 pi, but the new function, 0.5 of x, has only gone halfway. We've only gotten just the top portion. I actually have to move to the right just to see where the purple line actually finishes. And notice that it has a period of 4 pi. So then what's essentially happening here? Like what does it mean then when we're really talking about frequency and in terms of B? Well, the way that I like to kind of describe this is that the B is my frequency. It's telling me how fast or slow I'm completing cycles. All right, and so if you think about, especially because we're talking about a unit circle, the time it takes to complete one lap. If you have a consistent lap time, but then I say that you are going to double that, so your frequency is going to be 2, that means you're literally cutting your lap time in half. Well, what's the normal period for a sine or cosine function? Right? The normal period is 2 pi. Right? That's the normal lap time. That's how long it takes sine and cosine to finish. So if my frequency is now doubled, then I'm able to complete one cycle in half the time, or literally 2 pi divided by 2. My period is now pi. And in terms of the column and what we saw graphically, we get that. All right, well, what about when B is 3? What if I'm able to complete a lap 3 times as fast? So that's my frequency. Well, that means I'm able to take my original lap time and divide it by 3. Well, my normal period is 2 pi, but I'm now able to do that 3 times as fast, or do that lap in a third of the time. My period is 2 pi over 3. And so this makes sense then when we look at fractions in terms of 0.5, right? My frequency is now a half. Well, what does that mean in terms of this lapping and running a race? Well, if my frequency is 0.5, I'm going half as quickly. I'm going half as fast. I'm going slower than normal. I'm taking my original lap time and I'm dividing it by 0.5. Well, what does that actually do to your lap time? It's actually doubling it, right? If you were to do 2 pi divided by 0.5, this is going to give you 4 pi overall, and that's what we got for our period. And so the algebra kind of makes sense with that, and so that's why I kind of like to use that analogy. Well, notice we're essentially then coming up with a formula. Period is always going to be 2 pi divided by whatever your frequency is. So if I'm just doing a general B, then my period is always going to be 2 pi divided by B. That means my angular frequency is just B, whatever I'm being multiplied with in there. And so this is how we can go through and essentially determine how long it'll take this cycle to complete. This is how you horizontal stretch. And so in general then, I've got general graphing form here. I want to put all the information together into one single form. And it doesn't matter whether it's sine or cosine. All the variables are the same. So putting this all together, this is the graphing form for sine and cosine. It's a lot. And the way that you're going to be assessed on something like this is not that you necessarily have to create a free sketch, but you are either going to be given A, the equations, and I ask you to, given the equations, match them with a graph, or given a graph, write the equation. Right? So you need to be able to find the information and then interpret it into this graphing form and essentially plug and play. To give you kind of the cheat sheet for this again, what A represents is the amplitude. This is the height, or excuse me, the distance from the max or min to the middle. B is your frequency. Right, it's how many cycles in 2 pi. So that means if you want to find period, period is equal to 2 pi divided by b. All right, h represents your horizontal shift. And gives your starting x value. K represents your vertical shift. And this represents your midline, which is important in measuring out your amplitude. The last little caveat is that sine starts on the middle. Cosine starts at the max. So this kind of gives you your general graphing form and doing the pieces. I think I don't have an example set up. All right, so let me give you an example to go through, and so you can kind of I can at least give you one to go through and find the pieces of information for. So I'm going to pull one. You'll kind of see behind the scenes here. Let's pull one from my lesson plan. Let's do, this is the application. Let's do one of these. So this is one that you'll see in the modeling video on Friday, but let's just go ahead and look at one. Let's do one that's, this one's good. So let's do this one. Okay, so copy that. All right. Now the goal here is to take this trig graph, this wave, and I want to write, well, first let's find the information and then write an equation, write a sine or cosine. We're actually going to do both, so I'm going to show you how both works. And this will be the end of our video afterwards. All right, so the first thing I'm going to do is I'm going to find the middle. It's also a good time to explain the process. So I'm going to find the middle. All right, to find the middle again, you can locate the max, which is here, and you can locate the min, which is at -3. And then the middle has to be the average in between the two. All right, now for me, I'm going to go through and sketch it in because I can just see it, that the midline is at -1. So what that describes to us then is my K value. All right, now from here, we can actually figure out what the amplitude is. So that's the second thing that I always tend to find. The amplitude in this case is a length of 1, or excuse me, math is wrong. Amplitude is 2, because the length, the distance between the middle and the highest point is 2 steps. So there's my A value. The next thing that I'm going to go through and do is determine what my period is. This will help me in determining what my frequency is. So the period in this problem, I need to pick a point. Generally, I do this from max to max, min to min, or middle to middle, right? It just kind of depends on how I want to find or classify one complete cycle. Most people generally will choose max to max, right? What is the length between the crest and the wave? Because this represents one cycle. That line's going to bother me, so I'm going to fix it. This represents one cycle, which by definition then is one period. And so if I look, this dash mark right here, although it's not labeled, I know that it needs to be halfway in between -pi and -2 pi. So it's -3 pi over 2. And it goes to pi over 2. And that represents one complete cycle. So I need to find the distance between these 2 points. So I'm going to do pi over 2 minus -3 pi over 2 to get a period of 2 pi. And so if my period is 2 pi, according to my frequency from before, I know that period is always equal to 2 pi divided by b. Well, in this kind of problem here, especially since I know period and I want to know what the frequency is, I'm trying to solve for b. So it's really helpful then to look at this problem as p is equal to 2 pi over b, or b is equal to 2 pi divided by period. If I cross multiply, I can solve for either b or p. And so if I'm looking for frequency, which is b, I know I can do 2 pi divided by the period, which is 2 pi. My frequency is 1. So there's my b value. So I have b, I have a, and I have k. The final thing that's missing is my starting x value, which is my k, or excuse me, which is my h. And this really kind of depends on if we are modeling with sine or if we're modeling with cosine, because both functions start at different places. So for example, we need to decide at this moment, do I want to use sine or do I want to use cosine, right? If I want to use sine, then my h is when this function is in the middle and then is traveling north and going up. Well, that's happening here at 0. So for sine, my h would be 0. And now I can go through and fill it in based off of my general graphing form here. I would have y is equal to a, which is 2, sine x minus h, which is, sine parentheses b, which is 1, and then x minus h, which is 0, then close the parentheses, and then plus k, which is negative 1, which you could just write as just minus 1. And so in simplest form then this would just be 2 sine of x minus 1, which we actually graphed not too long ago. But if I want to use cosine, then my h, my starting x value, isn't when I'm in the middle, but when I'm at my maximum and then traveling down. Well, here, that max occurs at pi over 2. I've actually already got it marked. So what I could do then is let h be pi over 2 if I was going to look at cosine, and then go through and fill in everything outside of that. A is 2, b is 1, x minus h, which is pi over 2, and then minus 1. If I type this into Desmos and I type this into Desmos, they should result in the exact same graph. And what this shows us is that we can use sine or cosine with modeling. What determines which one I'm going to use is how I want to choose where my starting x value is and look at the wave. And this will play a big role as you're modeling and hopefully give you some really good practice in looking at sine or cosine when we model. All right, so take a look at the project description and attempt that. I'm here. The following class day will be virtual and give you an opportunity to ask questions for the project. I've got an example set up, so make sure you look at my work. It'll be a separate video where I'll just kind of explain where I got my data and then how I could play around with it in Desmos to find my midline amplitude, etc. So that's it for this video. Take a look at the practice problems as well, or take a look at the project, excuse me, and then practice problems will be in the next video 7, which is the next lesson, specifically looking at all of the examples for modeling and playing a lot more with this. But for now, start working on the applied problem in your project.